All right, let's start. Good morning. So this week we're going to transition to infinite sums series, initially of numbers. We're going to talk about convergences and divergences, various kinds of convergences of such things, and then so this is week 13. And then next week we're going to study infinite sums of functions. That's going to be week 14. And then that will be the end of the topics that we're going to cover for this class. In week 15, we have 2 classes, but I'm planning to do some sort of a review in those 2 days. So that will be it. So today I want to spend plenty of time on Taylor approximation, its statement, and the proof of it. Now, there are multiple sort of Taylor approximation theorems and so on. I'll mention what these are all about, but let's start as usual. I is a non-empty open interval, and here's sort of like a short review. If I have an n times differentiable function f on my interval I, and if I were to pick some base point x star, then I get to associate 2 new things to this point. One of them is this nth order Taylor polynomial of f at x star. This is like a shorthand notation, but all you do is you just add f of x star, so the 0th order term, plus f prime of x star times x minus x star, and so on, all the way up to the nth derivative of f at x star divided by n factorial times x minus x star raised to the power n. Okay. Now remember, last Friday we looked at the case when lowercase f was a polynomial function to begin with. If you start with a polynomial function, then you're just going to duplicate the function that you started with. Okay? That's the beauty of this whole thing. But the point of this is that you can, even if your function is not a polynomial function to begin with, you can just look at this Taylor polynomial. And in essence, this allows you to just start with any function to which differential calculus would apply and pretend that it is polynomial. Why is that a good thing? Because polynomial functions are algebraic objects, to say the least, and they are a lot more easy to calculate things with and so on, and also think about. They are a lot more rigid. So Taylor approximation is going to say us something about, oh, for this, that, the other thing purposes, I can just truncate higher order terms of my function according to the Taylor polynomial and just pretend that my function, which I initially assumed, say, 5 times differentiable, is in fact an order 5 or degree 5 polynomial. So that's the Taylor polynomial, okay? And the difference between the original function and the nth Taylor polynomial at x star is the nth remainder, okay? And so I can write f equals tn plus rn if you want. It's the same thing. And Taylor approximation is all about what this remainder is. This is the error. You want to control this guy. OK. Now, there are multiple sort of formulas and estimates and so on. I'm just going to stick to the 3, I think, that are stated in the textbook. There are many more. But we'll set that aside. So I take an n, non-negative number, integer, some function f, and a base point x star. So the first item is what is called the Peano form of the remainder. Okay? If f is continuous or n times differentiable, I had to say this because if n were equal to 0, this would just say that f is 0 times differentiable. But 0 times differentiable doesn't mean it is necessarily continuous. If you want to think of it in a slightly more, how to say, compact fashion, you can just say if f is Cn here. Although, say if n were equal to 2, what I say over there is not going to require that the second derivative is continuous. There's a small difference. There's a small sort of gap here. So if you want to be sort of fast about stating these things, you can just take in the first item the hypothesis to be f to be Cn, n times continuously differentiable. Okay. If f is like this, then the nth Taylor polynomial at x star is the unique polynomial function of degree at most n, because in principle, even though we're writing this t sub n as a priori a polynomial of degree n, it might be the case that some of the higher order derivatives vanish. And so it is not necessarily true that t sub n is for sure a polynomial of degree n, but it's at most n, okay? It's a unique polynomial function of degree n that is order n tangent to f at x star. At x star. Now, what does that mean? This was the content of one of the previous problems in a problem set. This just means this, okay? I'm going to compare f of x and Tn of x. Okay? Now, I want this to be little o of x minus x star raised to the power n. That's what it means for these two functions to be order n tangent. And so this means if I were to divide this by this, and if I were to take the limit as x goes to x star, I want this to be 0. That's what it means for the nth Taylor, so this function to be order n tangent to f. That's the definition. Okay. So if I had only differentiability of f, well, we had the order 1 tangency of the Taylor polynomial. But when n equals 1, t sub 1 is nothing but this expression. Right? And in fact, if you remember how I defined differentiability, I was always putting these two terms into one brackets, and that's how I even talked about differentiability here. I would write it like this. I needed this to be 0 as you take the limit. So all the way back in, I guess, week 8 or something, when we first defined differentiability, I was already using the Taylor polynomial format here. Okay? It was just that when you're talking about differentiability, it's all about the first Taylor polynomial, a polynomial of degree at most 1. Right? This is the equation of a line, if I were to fix x star. So now we're just trying to use, we're trying to make sense of higher order derivatives, and therefore we're sort of looking at a tangency relationship, but instead of looking at an order 1 tangency relationship, we're looking at higher order tangency. But these two limits are analogous in a sense. Okay, that's the first statement. And of course, at this point, what we can also say is that the numerator here, you see, is precisely the absolute value of the nth remainder at x. In other words, I can also say, as a consequence of this, is that the nth remainder is little o of the distance between x and x star raised to the power n. I'll write that too. Consequently, So little o of x minus x star in absolute value raised to the power n as x goes to x star. Okay. Now, what does this mean in terms of, practical matters? Because ultimately, the whole point of this whole thing is, f itself might be a complicated function, but a polynomial, in principle, will be a lot more simple. Okay? And so, so say f is 5 times differentiable. For whatever reason, you have this hypothesis coming from somewhere. Say in your model, you already require that your lowercase f is 5 times differentiable. Okay? Then, and let's say that you get to compute the fifth derivatives and so on, so that you have access to the fifth Taylor polynomial. It's a polynomial of degree at most 5. Well, you can write it like this then. And of course, in order for that to make sense, I should write it like this. Say you have access, you can compute the first 5 derivatives at x star. X star is this nice point that you were given somehow. You sort of figured out this data point is a nice point where f is nice. Okay? So you get to compute this. Therefore, you get to compute explicitly, okay, the fifth Taylor polynomial. So I have access to this polynomial. Okay? Let's say, honest to heavens, degree 5, at most degree 5, polynomial with real entries, real coefficients. Okay? This is a nice polynomial. You can do algebra. You can look at roots. You can do a bunch of things. But this fifth Taylor polynomial is not the function itself. Okay? It's not the same thing in principle. In applications, most functions are not polynomials. Okay? Most functions are also not necessarily differentiable, but never mind. We're assuming that most functions are differentiable here. And so this first item says this. Okay? You want to figure out what f of x is for x near x star. Say, in fact, x star is 0. Okay? So I chose x star to be 0. Well, then I have this up to x raised to the power 5. Something that decays faster than this. Okay? And so, for instance, if you were trying to figure out what f of 10 to the minus 1 is, you can just plug it here, and the order is going to be of the order 10 to the minus 5. Okay? So I'll write it here. So in this case, right, so you're looking at what f is at 0.1. You can instead plug this 10 to the minus 1, 0.1, into the fifth Taylor polynomial at 0. And that's going to give you some error, of course, but the error is going to be of the order 10 to the minus 5. So plus minus, let me say. Error margin is 10 to the minus 5. That's a pretty nice thing, you see. It's like, so you're trying to plug in something in the first digit after the radix. And the error this creates, instead of using f, the fifth Taylor approximation, or Taylor polynomial, creates an error only at the fifth digit. That's pretty nice. But of course, you see, the higher derivatives you have, the better the approximation, rightfully so. But at the same time, that's also going to require that you can compute higher derivatives at that point. So the more, the better the estimate you want, the more differentiability you're going to need, the more derivatives you're going to need to compute somehow. Okay? And when you think about it, computing derivatives too is, its own matter, right? It's a whole different can of worms. It requires limits. Okay? You cannot just, take something like this using a computer, say. And so all of these things sort of play with each other. But at least as a first approximation, say, that's a pretty nice, pretty optimistic thing to have. Okay. Any comments or questions about this? Yes?
Does the T represent Taylor
yes.
or tangent?
Taylor, both. Good. Both. At a higher level, you call this a jet, nth order jet. You use instead of T, J. But yes, ultimately, this is, you can also think of T sub n as the fifth or the nth order tangent as well. Either way, yeah, very good. Any other comments or questions? Okay, that's the item 1. Item 2 and item 3 are rather specific formulas, okay, for the nth remainder. This gives you an estimate, but you also want some sort of a formula. For formulas, typically you need more differentiability, okay? So instead of assuming n times differentiable, I'm going to assume n plus 1 times differentiable. Then I can represent, in fact, this remainder as an integral or as sort of like a mean value type expression. So this second one is called the integral form. And the third one is going to be called the Lagrange form. If f is n plus 1 times differentiable, then I can write it like so. Then for any x in I, right, this is equal to 1 over n factorial integral from x star to x, which in this case probably should be hk because I'm assuming only n plus 1 times differentiability. I'm not going to integrate the n plus first derivative of f by itself. I'm going to multiply it by some polynomial, and that polynomial is going to match with this. Hang on. This should be u. This should be u. D. Yes. Oh, maybe it's the other way around, actually. I always mix this up. X minus u. Like this. Okay. So that's a pretty nice formula. We'll talk about how this actually makes sense, because since I'm assuming that f is n plus 1 times differentiable, the n plus first derivative here is Newton integrable. Therefore, it is locally hk integrable. So we're going to use this by parts formula that we discussed, the baby by parts formula, that's going to tell us that this product itself is hk integrable, and we can apply the by parts here. So we're going to use that. Questions? And for the third item, I want to have something that is similar to MVT. I think I'll write it here. because I want to write all the parts of the Taylor approximation on one board. This third item is called the Lagrange form of the remainder. Again, I'm going to assume more than just n times differentiability. I'm going to assume n plus 1 times differentiable is n plus 1 times differentiable then for any x and I, if x is not the same thing as x star, implies there is some new point, x dagger, strictly between these 2 points. Such that, again, the nth remainder at x is exactly the n plus first derivative of f evaluated at this new point x dagger divided by the appropriate constant. Like this divided by this. Oh, times something. I forgot that something. Is equal to this. It has to depend on x after all. It's not a constant. Okay. Very nice. Any comments or questions about the statements of either one of these 3 items?
So the second and the third.
Yes.
Right? You want to write, for the second, you want to write f as t n plus 1
Exactly.
plus that.
Exactly.
And
Yes.
but and then the Rn form is a bit different.
The what form?
Rn.
Um,
Yeah, why don't you say that it's Rn plus 1?
here,
Yeah.
in order for me to be able to control the error coming from the n plus first derivative, I would need to assume that f is n plus 2 times differentiable.
Oh.
Yes. Exactly. That's a good point. So in this second item and the third item, you assume f is n plus 1 times differentiable. So in principle, you could look into the n plus first Taylor or the n plus first remainder. You can expand it. But then you lose the control there. Instead of expanding it like this, in which case you would have just an upper bound, you say, I'm not going to expand all the derivatives I have available. I'm going to expand all the way up to n, and then the remainder is going to be once differentiable. Okay? So if f is n plus 1 times differentiable, R sub n is going to involve at most the nth derivative of f. Okay? Consequently, R sub n, this remainder function itself, will be once differentiable. That I'm going to use to turn into explicit formulas.
So you have an f that is, in fact, n plus 2
Nope.
differentiable?
Nope. the integers here are somewhat confusing, I realize. But for instance, let me put it this way, OK? The main complication here in this Taylor approximation is the index management. So you're right to question this. And again, here, instead of just assuming that f is n plus 1 times differentiable, I could have assumed Cn plus 1, and here too, Cn plus 1. But anyway, so for instance, first item, say n equals 0. OK? So f is at least continuous. Maybe I should have said n here, actually, so that it works. If n is 0, the 0th polynomial of f at x star is nothing but f of x star. It's a constant polynomial, degree 0 polynomial. OK? In order for that to be tangent to f of order 0, that is the same thing as saying that f is continuous there. OK? If I were to plug in n equals 1 here in the Peano part, this is the first order Taylor. That is the first order polynomial that you use in the differentiability. OK? So that's what it boils down to. Here, if I were to plug in n equals 0, OK, this is going to tell me f needs to be 1 times differentiable. So plug in the second item, n equals 0. So f is once differentiable. And what does this say? The 0th remainder is an integral. What is the 0th remainder? It's nothing but f of x minus f of x star. So OK. This is the function itself. This is the 0th order Taylor. This is the 0th remainder. When I plug in n equals 0 here, this is just 1, goes away. This drops out. This is nothing but the integral of the first derivative. But that's just a fundamental theorem of calculus. So somehow the second item is fundamental theorem of calculus sort of generalized to higher order derivatives. OK? That's how we can remember this as well. Does this make sense? And again, if in the third item, if I were to plug in n equals 0, I'm assuming that f is differentiable. And I'm saying that the 0th order remainder, which is f of x minus f of x star, equals, I'll write it here too, in the item 3, if I'm assuming that n equals 0, that means that I require that f is differentiable. What does it say? Given any x that is not x star, there is some point in between x dagger such that, what is it? So on the left-hand side, I have the 0th remainder. Again, this is nothing but f of x minus f of x star. And what do I have on the right-hand side? F prime at x dagger divided by 1 factorial. 1 factorial is just 1. That drops out. N is 0, which means this is nothing but x minus x star. Oh, it's like this. Times x minus x star. This is literally mean value theorem. OK? So Peano form is pretty much a definition of differentiability adapted to higher order derivatives. Integral form is pretty much FTC1, first fundamental theorem of calculus, applied to higher order derivatives. And the Lagrange form is nothing but mean value theorem applied to higher order derivatives. Okay. And I hope at this point you look at this, and if you try to think about how to prove these things, you sort of think about some sort of an induction probably. Induction on the number of differentiability. Does this make sense? Okay. Any other comments or questions before I transition to proofs? Okay. And you are right, of course. We're going to take these ideas, and we're going to basically do some sort of a induction on the number of differentiability. Let's start with 1. Okay. So I need to show two things, in fact, here. Okay. And also, I can assume that n is at least 1, because when n is 0, I have that f is continuous, and that's the definition of continuity. Without loss of generality, we can assume n is at least 1. Okay. Now, I need to prove two things, like I was saying. First, that this polynomial, okay, is tangent to the graph of f at x star of order n. And furthermore, I need to show that it's the unique such polynomial. In fact, you've done this uniqueness part, at least for n equals 1 in one of these previous problem sets. We're just going to do the same argument, essentially. But we need to show tangency. Okay. Okay. So here's the important part, okay? We had seen this in the example last week as well. But this polynomial is a very special polynomial in that its first n derivatives at x star match with those of f. Okay? I'll leave this as an exercise if this is not clear to you. For any k between 0 and n, if I were to take the nth Taylor polynomial at x star, differentiate it k times, and then evaluate this at x star, I'm just going to get the kth derivative of f evaluated at x star. This is essentially the reason why in the Taylor polynomial we have those factorials in the denominator. If we didn't put those there, this wouldn't match up. But if this is the case, that means that all derivatives all the way up to n of the nth remainder, which is just the difference between these two, is 0 at x star. So in a sense, this is a very flat function to begin with. Okay? Now, one step at a time, what I want to do is I want to apply mean value theorem to this remainder. So for instance, what I can do is this. I can assume, again, x is not the same thing as x star, because I know that the nth remainder at x star, if I were to plug in x equals x star here, is going to be 0. It's not going to be 0, but for this little o thing, I don't need to take x to be exactly equal to x star. I need to be arbitrarily close. So what I can do is this. Okay. This is what I'm trying to control. As usual, I start from the end. I start from the thing that I'm trying to control. Nth remainder, exactly. Nth remainder at x star itself is 0, because it's just the 0th order derivative. So I can write it like this. This is 0. For k equals 0, this is just a function at that point. But then I can apply the mean value theorem to the nth remainder, which I know to be differentiable. Okay. And I can write it like this. Say x1 in absolute value times x minus x star in absolute value for some x1 between x and x dagger, x and x star. By mean value theorem applied to the nth remainder. So here's the picture. Here's my base point, x star. Here's x. I'm applying mean value theorem to the nth remainder function, which I know to be differentiable many times, between these 2 points in order to obtain some point x1 in between such that the rise over run, so this divided by this, is actuated by the derivative. I just apply the mean value theorem. Okay? Now I'm going to keep going. Okay? Now I'm going to apply the mean value theorem to the first derivative of the nth remainder between these 2 points. That's going to give me another point, and so on. I'm going to keep going. That's the idea. Write it here. Oh, maybe I should put something here. Okay, I'm going to continue from here. Red star. See, the trick here again is that the first derivative of the nth remainder evaluated at x star also is 0. So I can subtract that expression from this part over here and apply mean value theorem to the first derivative. Okay, so like this. Nth remainder derivative at x1 minus nth derivative at x star in absolute value times this guy. Again, this is 0. That's why I can do it. But again, by the mean value theorem, I have some other point here. Okay. Such that the first derivative of the first derivative, in other words, the second derivative of the nth remainder, at x2 times, this time I'm going to get yet another thing coming from x1. Okay. And you keep going like this. And finally, you're left with, I want to do it all the way up to the n minus first derivative because I want to use the nth derivative to get some estimates. This will be n minus 1 minus like so. And then I have a bunch of factors here. I should have n minus 2 minus x star dot 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 x1 minus x star times x minus x star. Nice. But then I can divide this by x sub n minus 1 minus x star in absolute value, and then have another factor here, and write it like this. Times I have okay. The formulas are complicated. All I did was this. Just recapitulate. I started with x star and x, two distinct points. I applied mean value theorem to the nth remainder to get some x1 in between, such that the rise over run is actuated. Then I applied the mean value theorem to the first derivative of the remainder between these 2 points, and I got another point in between. And I keep doing this many times. Okay. X1, X2. Mean value theorem at each point is going to give you some point in between the endpoints that you're using this at. Okay. Now here's a point. I have a bunch of factors here, but each of these indexed points that I generated using mean value theorem, so for each of these, this distance is something like this. They're all upper bounded by the initial distance between x and x star, which means that this factor is bounded by x minus x star raised to the power n. And since I also know that as I take x to x star, okay, all of these points that I chose, that I obtained using mean value theorem, 2 are going to converge to x star. And since the nth derivative is differentiable, this ratio has to converge. Consequently, this is epsilon times x minus x star raised to the power n, which is what I wanted. So consequently, what did we do? We basically used mean value theorem a bunch of times. We applied it to derivatives of the remainder. Okay. To really understand these proofs, I would highly recommend that you do it for n equals 2, for instance. So it looks like it's daunting and like I'm sort of juggling a bunch of derivatives and stuff like that, but it's really not that sophisticated underneath. It's a matter. It's a complicated matter, of course, to control these indices and stuff like that too. But that's a sort of different matter as far as I'm concerned. Index management. Okay. That's the first item. Any comments or questions about this? I will probably take part of tomorrow as well to do this, to complete the proof. Oh, so this is the existence. Let's say a couple words about the uniqueness. So far, we showed that this nth Taylor polynomial is indeed order n tangent to f at x star. But we want to show that there's no other polynomial that does this. Okay? What you can do here is you can take any two polynomials of degree at most n, and you can show that if they are order n tangent, in fact, these two polynomials have to be the same polynomial. Let's do it here. So far we showed tangency of order n. Take two polynomials, x minus x star raised to the power k, bk x minus x star raised to the power k. Say you have two polynomial functions like this that are order n tangent at x star. You're assuming this. I want to show that p has to be the same thing as the same polynomial as q, which consequently would allow me to conclude that the nth Taylor polynomial is the unique nth order or unique polynomial of degree at most n that is tangent of order n to f at x star. What does this mean? Well, I'm just going to look at the difference between these two, right? Divided by x minus x star raised to the power n, and I'm assuming that that limit goes to 0. I'll write it like this. That's the expression I want to go to 0, or I'm assuming that it goes to 0. But then when you reorganize this, you get this. Like this, like this. Triangular allows me to put the absolute values inside. And then I can distribute this as well. Like so. Okay. Raised to the power n. I'm assuming that this goes to 0. That's what it means for these two to be tangent. You're going to realize this is of the form, well, a0 minus b0 divided by x minus x star raised to the power n plus dot 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 plus a sub n minus 1 minus b sub n minus 1 in absolute value divided by x minus x star like this, and then the top order terms. Just give me 2 seconds. That's that. You're saying that this has to go to 0. In order for that to go to 0, all of these blow up initially. In order for them to not blow up, the numerators have to be 0 to begin with. And then in order for the limit to be 0, this has to match to this. And that gives you uniqueness. OK, apologize for taking your time, going over time. But we're done with the proof of the first item. Tomorrow we'll do the second and the third proofs. Thank you. All right, let's start. Good morning. I'm going to take attendance today. I want to finish the proof of Taylor approximation. I think I'm going to fast forward some items. I'm going to tell you the main line of attack, and I'm going to leave certain calculations to you to verify. And then we're going to switch to infinite sums, And indeed, I want to first go back to sequences and talk about this Cauchy property that I kind of mentioned. I told you that for sequences of real numbers, as well as for sequences of functions, Cauchy property is the same thing as convergent. So sequence is Cauchy if and only if it is convergent. So we could just bypass this Cauchy property for convergence purposes. But now, since we're going to look into specific types of sequences where the sequences are made up of partial sums, this Cauchy property is going to be rather important for us. So I want to spend time on discussing that. So let me go ahead and discuss certain items. The usual assumption is still there. I is a non-empty open interval. Let's leave this aside for a while. I'm going to get back to it. Taylor approximation was all about assuming that your function is differentiable many times. And based on how many different derivatives you have, you sort of differentiate your function and associate to your function at any point given a polynomial. That was a Taylor polynomial T sub n. Right, so this was this. Like so, 2. X star raised to the power 2. I'll write one more. Third derivative at x star divided by 3 factorial is 6. X minus x star raised to the power 3 and so on. Okay. So continuity was all about this 0th order term. Differentiability was about the first 2 terms. We haven't really used the second one, but if you think about some of the items you discussed, you looked into in Calc 1, for instance, you have like the second derivative test. You would look at the second derivative of a function. You would see if it is positive or negative. That would tell you, oh, the function is concave, convex, whatever. So for instance, the second derivative test would be about understanding the second order term. In multivariable calculus too, there's a similar thing. So if my function f were multivariable, this f double prime would be a matrix, or something more general than that. And again, you would look at, you would have some sort of a second derivative test. You would look at a certain expression made up of second partials, and that would give you, this is what's called the Hessian whatever, that would give you, again, some sort of a concavity property. And in geometry, too, there are notions like curvature. Many ideas of curvature are, again, second-order terms. Tells you something about how much the graph of a function, let's say, is bending. And then there are further and further sort of orders that, throughout the sciences, end up being useful in different contexts. Of course, the second derivative is also the acceleration. You can think of it that way, too. So all of these orders, on the one hand, can be associated to one function, or they can be sort of considered by themselves. And depending on the situation, assuming that you have sufficiently many derivatives of your function, you would just look at this Taylor polynomial, and I should probably end this at the correct term. Now this ends at the nth derivative, n factorial, x minus x star raised to the power n. And so you would just look at the first n terms, say the first 2 terms or the first 3 terms, whatever, or 4 terms. And that would sort of allow you to approximate the sort of use a polynomial instead of the more complicated function. Right, so just to give an example, this is a nice example. So if my function is e to the x, there are multiple ways to define this. The definition I like to think of it as the unique solution of a certain initial value problem. For instance, that's an initial value problem. This is a first order ordinary differential equation. You're saying, I want one function such that its derivative is equal to itself. And at 0, it gives you the value 1. You can use fundamental theorem of calculus, whatever. So this will sort of give you some sort of a recursive relationship. And whatever the solution of this is, that we call the e to the x function. OK? But this is like a complicated function, of course. But what you can do is you can look at its Taylor polynomials. Right? Because since you know that any derivative of f is itself, well, this is just going to be, say, at 0. Right? So for any k, the kth derivative of this specific function at 0 is going to be just 1, which means the Taylor polynomial at 0 of the exponential function is going to be nothing but k from 0 to n, x raised to the power n divided by n factorial. Right. Maybe you've seen the definition of this exponential as the limit of this, of course. We're going to get there, OK? So ultimately, we want to say eventually something like this. If my function is infinitely differentiable, like this case, then for any n, I have a Taylor polynomial of order n. OK? So in a sense, I have a sequence of polynomials as functions. And certainly, in order for me to be able to say t sub infinity of f at 0 is f itself, I need to take this and take n to infinity somehow, in some sense. These are functions, so I should worry about pointwise or uniform convergence or whatever. And then, insofar as indeed I can take the limit as n goes to infinity of this expression, and insofar as I can recover the original function that I started with, I'm going to call such functions real analytic. OK, so these are going to be even more specialized functions compared to infinitely differentiable functions. So for instance, in a previous problem set, you looked at this example. This is one of those so-called bump functions. These are very smooth. Something like this. What was it? E to the minus 1 over x squared. You showed that this is infinitely differentiable. At the origin, any of its derivatives is 0. So this is a very flat function, which means that for any n, the Taylor polynomial of this at 0 is 0. OK? This is the, so the nth polynomial of this function at 0 is 0, is a polynomial that is constantly 0. So you see, for this function, something is going very wrong here. Even though I can look at the sequence of Taylors, if I were to look at this infinite sum, I'm just adding 0 infinitely many times to itself. It's going to be 0. So I'm not going to be able to recover f itself. You see, this is not going to be an analytic function. This is just going to be C infinity, infinitely differentiable. But whether or not the Taylor polynomials converge to the original function is going to be a more specialized concept. And we're going to denote that by C to the omega, real analytic. Just to give you a sense, the reason why we also emphasize this real analytic is because we can also do a lot of these things in the complex setting. So for instance, you can just take x to be a complex number. That would be just analytic function. But remember, a long time ago, when we were discussing these completeness axioms, whatever, I told you that there are different flavors of analysis. What we're doing is real analysis, and there's also complex analysis. When it comes to complex analysis, somehow embedded in it, in complex analysis, is already a certain first-order PDE. This is what's called the Cauchy-Riemann equations. And since, for whatever reason, complex analysis comes endowed with a certain PDE, it turns out, for instance, that in the world of complex analysis, differentiable functions are the same thing as functions that have analytic expansions like this. So in the world of complex analysis, 5 times differentiable, 6 times differentiable, all of these sort of pesky details that we're dealing with in real analysis, they just like vanish. Either something is not differentiable. If it is differentiable, it has a power series expansion in complex analysis. It's a very different world, as you see. I'm just letting you know. That's why people often use the phrase real analytic instead of just analytic. When people say analytic, that's probably in the world of complex analysis. So there's a distinction there. Anyway, so I would also highly recommend that you take a complex analysis course after this. You're certainly ready. OK, so let me remind you of the Taylor approximation theorem. OK, so I have a non-negative integer n. That's going to be my number of differentiability. I have some function taking real values defined on my open interval I, and I'm choosing some base point x star. And the point of this Taylor approximation was all about the discrepancy between the nth Taylor polynomial and the function itself, and this was the nth Taylor remainder, f minus this. So what is R sub n then? R sub n is the cost of thinking of lowercase f as a polynomial given by the Taylor. OK, that's the cost. OK. So the zero is a Peano form of the remainder says this. If I have a continuous function and it is n times differentiable, if n is 1, of course, this is redundant, then the nth Taylor polynomial is the unique polynomial function of degree at most n, that is order n tangent to f at x star. OK. So for instance, if you were to look at this, this case, for any n, the order n Taylor polynomial is degree 0. So nth Taylor polynomial, in general, doesn't need to be a degree n polynomial. It's just that you have an upper bound on the degree. Degree at most n, that is order n tangent to f at x star. And therefore, since R sub n is f minus t sub n, I'm saying this is little law of the distance between x and x star raised to the power n. That's the Peano form of the remainder. The second is the so-called integral form of the remainder. I tried to figure out who first came up with the form, but I couldn't find it. So we're just writing it as integral form. Integral form of the remainder. Now I'm going to assume that f is n plus 1 times differentiable. And based on that, I would like to be able to represent the nth remainder as an integral. OK, so if f is n plus 1 times differentiable, then I'll write it here. I can represent, then for any x in I can represent the nth remainder at the point x as a certain integral, which is this. This is not very easy to remember initially, but there's a pattern. OK. So x minus u raised to the power n, f differentiated n plus 1 times of u du. OK. So that's the integral form. I won't say more about how to remember this. For now, I think it's good to leave it as sort of like a mysterious matter. But this does sort of fit into a larger pattern. Okay? And the third is, even though there are many other sort of formulas for the remainder, the one that is discussed in the textbook is the Lagrange form. Okay, and it says this. Again, I'm assuming more differentiability. If f is n plus 1 times differentiable, then for any x and I that is distinct from the base points, okay, if x is not the same thing as x star, then there is some new point x dagger strictly between x and x star, okay, such that the nth remainder evaluated at x is the n plus first derivative of f evaluated at this new point divided by n plus 1 factorial times x minus x star raised to the power n plus 1. Okay. And we kind of discussed all this stuff. What is the Peano form generalizing? It's generalizing basic to the definition of continuity when n equals 0 or differentiability when n equals 1. Integral form generalizes FTC1. Lagrange form generalizes mean value theorem. Okay? And I wanted to say one final thing, because I remember when I first was learning about these kind of things, I really disliked thinking about the remainder. I would be, I would get confused. Like, why am I not writing it as f minus the polynomial, whatever? So if you're like me, I would suggest that you write it out a couple times explicitly, and then eventually it clicks. And as I've gotten more experience in this business, I started liking sort of separating out the remainder more and more. And just to tell you what this is about, I'm just going to expand it, okay? So this says f minus the nth Taylor equals this. So solving for f tells me this. F of x equals this. Oh, the first derivative. Like this. Double prime at x star divided by 2, x minus x star, all the way up to the nth derivative. Okay, so everything is nice until here. Oh, that's n. And then you have the n plus first derivative at x star again. Okay. But if I'm expanding this way, of course I need to assume that f is n plus 1 times differentiable. Peano form would give me that the error here would be of the order n plus 1. Okay? So this is given to me if I apply Peano for an f that is n plus 1 times differentiable. But item 3 says, oh, if you don't want this, okay, What you can do is you can be a little bit more frugal in the order of your polynomials, and you would be, you would contain yourself. You would not expand all the way up to n plus 1. You would truncate your expansion here, but instead of this, now you have something else. You almost have this, okay? Except the only trade-off is that this point where you're going to evaluate your derivative is going to be not the base point that you were looking into. Some other point. That's what the Lagrange says. Okay? I should say one more thing. If on top of that, your function f was Cn plus 1, that is to say, not only was it n plus 1 times differentiable, but furthermore, the n plus first derivative was continuous. Okay? That's more assumptions. You're assuming more. Then what you can say is that since, in this case, the n plus first derivative is continuous, and since we know continuous implies locally bounded, you can get rid of this x dagger. You would just say plus big O of this. So if you're going to go for Peano with n plus 1 times differentiable, that's going to give you little o of distance raised to the power n. So the remainder decays faster than h to the n. But if you have Cn plus 1, you can say more. You can say not only is the remainder to the order n, so decays faster than n, but in fact, it decays at least as fast as n plus 1. So it doesn't decay like n plus 1/2. That's sort of the difference. Okay. So you see all of these estimates end up being useful in different contexts. You may not sort of appreciate these minute details, but I'll tell you, like this is such a convenient thing to be able to do. Any comments or questions about the statements?
What is plus half? What does it mean?
Yeah, so here, raised to the power n plus 1/2.
It's big O?
No. I'm saying if I have the remainder like this, okay, so this remainder could be to the order distance raised to the power n plus 1/2.
Piano form is little o, right?
Yeah, sure. Let me put it this way. Apply the Peano form to it, to this, for n equals 0. Okay? For n equals 0, Peano form just says that as x goes to 0, this goes to 0. That's fine because this is a continuous function. The remainder decays faster than distance raised to the power 0. That is to say, it decays faster than 1. That is to say, it decays. But in fact, it decays to the order 1/2. It decays faster. So when you're sort of trying to come up with these estimates, you want to be, as sharp as possible. So it's like I can say, for instance, the remainder here. So compare this raised to the power 1/3. This, you see, this decays and this decays as well. But this decays faster than this does. Oh, it's the other way around. This decays faster than this does. So this is little o of x raised to the power 1 over 3. This is little o of x raised to the power 1/2.
What confuses me
Yes.
about this is that you always have to give us where you are expanding.
Yes.
Where is it?
0. There is again some technical issue here because x to the 1/2 is not defined for negative x values. So this is not quite defined on an open interval, blah, blah, blah. But for this, I'm looking at one-sided. So you see, this is the beauty of like doing things in the pure abstract manner. You can just set aside all these complications and sort of write down a general sort of like thing that actually doesn't apply most of the time. You just need to fudge around a little bit and so on. Okay. What's the point of this discussion? Well, the discussion here tells you that Taylor approximation is going to create less error for this. Less error for this function compared to this function. So you have to be more careful with this than this.
One more question.
Yes. Oh, it should be the other way around, actually. This is better. Yeah.
You switch little o to big O.
Yes.
Don't you?
Yes.
Right. And then power remain the same, n plus 1?
Yes. Exactly. Exactly. Yes. So in the Peano form, okay, n times differentiable would look at the nth remainder. N times differentiable would allow me to say little o raised to the power n. But if I have more differentiability, if my function is better, not only can I say the error decays faster than n does, or h to the n does, but in fact I'm saying it decays at least as fast as this. That's what I was trying to say here.
Under the condition, if the function is better.
Exactly. Yes. Well, I mean, you have to pay somehow. There's a cost to things. By the way, there are sort of like backwards directions of these as well. So you want to sort of convert these statements. Maybe you want to say, if you have something like this for some polynomial, then function is n times differentiable. There are versions like this. But, and I wanted to discuss some of them, but it's going to take more time. So we're going to set that aside. This is like all within the context of what is called function construction. Based on sort of some derivative data, you sort of put them together and reconstruct your function and so on. But let's set that aside. Okay. Any other comments before I start going back to the proofs? If you had done one, let's go with do the second one. So I'm going to do some sort of an integral, some sort of an induction. I want to induct on n, the number of differentiability. Instead of saying, oh, for n equals 0, this happens, and then if it is true for arbitrary n, then it is also true for n plus 1. Let me try to start from the end, like I do usually, and then what the induction, how the induction should be operated is going to be clear. So proof of 2. Okay. Now, of course, here, when you look at the statement, I didn't write it out explicitly, but implicitly, the statement is also stating that what you're trying to integrate, according to Hk, is Hk integrable. So that's actually part of the statements we need to verify. Now, I should ask you, how can I justify that this integral makes sense indeed? If I see something like this, what can I try using, perhaps? By parts. It's the product of two nice-looking functions, OK? When you're trying to integrate the product of two functions, that's by parts. And in fact, when you look at this, well, OK, let's try to put some variables here. So by parts, the baby version that we discussed is going to be sufficient in this case. So what do I want to do? Somehow, I want to relate the same formula for n derivatives. So somehow, I want to peel off one of the derivatives here and transfer it over here. OK? So this should be the dv part, and this should be the u part. OK, let's write it like that then. Capital A of u is going to be, no, maybe it's the other way around, actually. Sorry. I want to think of this as a derivative so that I can transfer one of the derivatives to the other side. So capital A is going to be the other part. X is fixed. I'm thinking of these as functions of u. OK? That's my capital A function. Lowercase b function is going to be the n plus first derivative of f. Lowercase a is the derivative of this guy. According to you, x is fixed. What is the derivative of this? N times this times the derivative of the thing inside. So that's a minus. So that's going to give me minus n x minus u raised to the power n minus 1. Okay. For at least n equals 1, of course. If n were 0, this would not quite make sense, but we're not going to use it there. So maybe I should be clear here too. I want this lowercase b to be the derivative of some uppercase b. Okay. What's a capital B that would work here? Well, the f derivative. Okay. And so, with these, what can I say? Let's just start with this integral, and we'll do some formal calculations, and then after we're done with the calculations, we're going to figure out when it is legitimate for those calculations to make sense. We're going to apply the same reasoning when we transition to series as well. We're going to do something very bizarre, namely that we're going to look at infinite series and stuff as if they are convergent without verifying that they're convergent first. And then we're going to do some other things, and then we're going to realize, oh, everything we did so far actually makes sense. That's what we're going to do later too. So if I start with this expression, okay, okay, this is this. I'm just looking at this integral. Let's not worry about whether or not this makes sense, whatever. We're going to make sense of that in a second. So if I use these variables here, what does this turn into? This x, capital A, u, lowercase b, du. Insofar as this makes sense, and I can apply by parts, this should turn into this. Okay. Capital A times capital B evaluated at the endpoints. minus integral of lowercase a, uppercase b. That's by parts. We're for now assuming that everything works. Now, what is this expression? Note that if I were to plug in u equals x, which is this bound, a is going to be 0. So that part drops out. All I need to look there, therefore, is minus when u equals x star. OK? Let's write it. Minus x minus x star raised to the power n. OK? And then nth derivative of f at x star. And then this. Here I have this expression, and uppercase b is nth derivative. I can take this constant out to get this. And then here I have x minus 1 raised to the power n minus 1 times, x minus u here. Nth derivative du. Distributing, I have this. Yeah. Exactly, very nice. So I have here 1n, and I have in the denominator n factorial, which means I'm going to have here plus 1 over n minus 1 factorial, and then this integral. This is the type of calculus I like doing. So nice. OK? What else can I do? Well, I can realize that this is the n minus first remainder minus the nth remainder, because the only difference between the two remainders is going to be this top term. And then this integral. So much fun. OK? Pretty nice. But you see, I'm trying to get some sort of a recursive relationship. I'm making a plus minus mistake somewhere, I think. This should be the other way around, I think. Yeah, we'll check. Do you guys see any mistakes here?
I believe you dropped the sign on the third line of the calculation, I believe. That's
Where?
where, with moving over to the integral, you forgot to place any sign, so the next line down will put a plus.
Here?
Oh, 8. You've just left it as a product, when it should be a difference still.
What should be a difference?
From you turn the difference into a product.
Oh, this difference
Mm-hmm.
turned into a plus?
But that sign should be kept with that integral on the right side.
No, but I'm getting another plus here, minus here.
Ah, that's why.
Yeah.
That's fun.
Yeah. So here's what I'm trying to here's what I'm trying to do. Okay, I want to think of this as something that depends on n. Okay, so if this is like n, this is pretty much the same thing except at n minus 1. Thinking of it as a function of n. Ultimately, I'm trying to show that the nth remainder is the same thing as I sub n here, you see? And so I would rather have this a plus and this a minus, in which case things would work the way I want them to. Let me see, maybe I made a mistake somewhere here. Let's try to do it again. So a of x, that's fine, minus a of x star b of x star, okay, minus x star raised to the power n, and then nth derivative at x star. Seems correct. And indeed, this is going to give me, oh, I made a mistake here, I think. Okay. Exactly, okay, I made a sign error here. That's the only difference. Here's why. Because this is going to be f minus all the derivatives, right? So like this, minus the nth derivative term, whatever. And this is n minus 1. And since I was looking into this, this should be r sub n minus r sub n minus 1. So everything is correct. The only difference is that I made this plus minus error. In any event, what I have ultimately is I can solve, so I can collect the n terms on the one side and the n minus 1 terms on the other side. I'll continue here. Apologize. So what do I have? This minus this equals this minus this. For any n at least 1, insofar as these integrals are well defined. Okay? And so this difference is independent of n. For n equals 0, that's going to be my base step. I know that r sub 0 equals I sub 0 by the first fundamental theorem of calculus. And by induction, if it works for n minus 1, it's going to work for n also. And again, by parts, tells me that this is integrable, this product, if and only if this is integrable. So I'm going to be able to carry it all the way through to whatever n I'm given. Okay. That's how you prove it. Really nice. So you set up this induction relation that carries you through. Okay. Any comments or questions about this? Now for the final statements, we have a couple of different options, okay? One option is this. If I assume a little bit more, that is to say, if I assume that f is not only n plus 1 times differentiable, but in fact Cn plus 1, so the n plus first derivative is also continuous, then I can apply this mean value theorem from one of the previous problem sets using the second item. So I can take this expression, okay, and apply this idea that if I have one continuous function and one Riemann integrable function that is on one side of 0, so this would be, for instance, a Riemann integrable function that is positive or negative based on the case. So in this expression, I could take psi to be this function and phi to be this function and take it out that way. I can do that. Now, as far as I know, this statement requires that this function that you're trying to take out of the integral is continuous, which means we can't quite use this method for a function that is n plus 1 times differentiable. Although I'm perhaps thinking that maybe instead of trying to pull out of the integral a continuous function, we can also do the same thing with Newton integrable. I'm not quite sure, but that's a nice exercise. I should mention here too, instead of Riemann integrables and whatever, you can use Hake integrables. That's fine as well, but that's not going to help us in this case. So if I assume at the very least f is n plus 1 times differentiable, I can apply this mean value theorem that we discussed before, or that was in a previous problem set. If not, I can apply some sort of a role lemma. There are multiple methods. I'll just tell you one function that our textbook uses. Just look at this function and apply role lemma. Magically, it gives you this. X star x minus y divided by x minus x star raised to the power n plus 1. Critical points of phi give you Lagrange formula. Okay. I think I will leave this to you because I want to move on with series. It's just a matter of calculation. You just differentiate this according to, with respect to y, and you look at the critical values. You realize you can apply the role lemma to it. That gives you directly Lagrange formula. Okay. So these are two different methods for 3, and I think it's a good place to stop for today. And we're done with Taylor approximation. Thank you. All right, let's start. Good morning. So today we're going to read a transition to series. I'm going to take attendance. Yesterday we finished the discussion of the Taylor approximation, multiple different formulas for the remainder. And I told you I looked up who came up with the integral form of the remainder. And then it turns out that it's in fact Lagrange as well. So look, there's a Lagrange form, but the integral form was discovered by Lagrange also. And I went down the history rabbit hole a little bit. So usually throughout this course, even though I seem to be sort of saying historical things, it was more like a story that I was just like speculating or reconstructing the history. This time I did my homework a little bit more accurately. I wanted to say a couple of things as to how this came to be. So, okay, I even wrote down the names. So, in 1712, okay, I'll write the name of the thing, Commercium Epistolicum. Okay, this is a Latin document because back in the day, even though this was published in the UK, the language of science was Latin, so they were writing in Latin. So this was the report that the Royal Society in the UK published to finalize the discussion, the dispute of whether or not it was Leibniz or Newton who came up with differential calculus first. Okay, and Taylor served in this. Okay, Taylor was in the committee that wrote this. And then 3 years later, he wrote this book, Methodus Incrementorum Directa et Inversa. So inverse, direct and inverse method of increments. I'm not going to write the name, but he published this book 3 years later. Oops. Where he published Taylor series, Taylor approximation, and perhaps more importantly, even though it's related, the method of what is called finite elements. So in PDEs, for instance, or differential equations, what you would do is instead of trying to solve a differential equation, you would just look at an arbitrarily small h as your increment, and so you would discretize your PDE or ODE, whatever, and solve that discretized solution. With the hope that, you know, if you were to take h to 0, you get a true solution, whatever. At the time, of course, people were not using computers, but this is really the foundation of simulations of PDEs or approximating PDEs and stuff using computers. Presumably, he was only looking at ODEs, but never mind. Now, at the time this was published, and Taylor was not using the language of functions, whatever. At the time, people did not realize these were supposed to be functions, whatever. He was using the phrase fluxions, okay? And it was somewhat murky what was happening. And in a sense, the contemporary scientists and mathematicians at the time didn't quite understand what he was doing. So this work was considered obscure and went dormant. It took around like 60 years for Lagrange to go back and realize, oh, hang on a minute, there's something here. And in 1772, so Lagrange is French, he realizes, oh, this Taylor approximation, Taylor series business is the real deal. And in fact, it's the foundation of differential calculus. And so here, Lagrange realizes, oh, you can write the remainder as an integral or in the Lagrange form, whatever. Okay? It's funny. So the conclusion of this report is that it was Newton who found it, this differential calculus. So now I should ask you, who do you think was the president of the Royal Society at the time? Newton was the president of the Royal Society, And he came up with a committee that was, in his side. Like Taylor was like a friend of Newton and other people, and they came up with a couple of French people, De Moivre and stuff like that, who agreed with Newton also. So they found a couple of scientists who liked Newton more than Leibniz. And the final verdict was that Leibniz was a plagiarist. And it seems part of why this Taylor approximation, it took so long for people to realize that this is something important, was because while people thought in the continental Europe that Taylor was biased and probably he doesn't understand math that much and all that stuff. Okay, so Taylor was somewhat blackballed as far as I understand. So funny historical matters. Which I'll submit to you that similar sort of petty drama happens today in sciences. Of course, us regular people don't quite know these kind of things. I'm talking about like the upper echelons of the sciences. And of course, especially math, pure math and stuff like that, the institution has a vested interest in making us and you believe that we're sort of these enlightened people, but not quite, you see. It's like we're all scoundrels and stuff. Anyway, just wanted to mention this. Very fascinating, I find, the historical matters like this, even though, I'm not quite a historian, and I often take sort of liberties in sort of restructuring the story. Yeah, so in terms of our different integral theories that we discussed, so we discussed Bourbaki, Riemann, Lebesgue, Newton, Hake. So Bourbaki is, in fact, a group of French mathematicians. It's not one person. So that's continental. Riemann, of course, is German, continental. Lebesgue, continental. Although some would argue that you probably should be splitting German and French also. They also sort of like bicker between each other. Newton certainly is British. Hake, so Henstock, he's either British or Irish. I think he used to work in a university in Northern Ireland. So let's call B. But Kurzweil was Czech, so that's again continental. So it's kind of like, balanced in terms of the types of integration theories that we discussed. Anyway, just wanted to mention. Oh, but of course, Hk integrals were initially conceived by Danjois, and Danjois was French. He was very French, so make of that what you will. Anyway, that's like a little tidbit of history. And I'll say this too. It's like for these kind of matters, I really find AI very convenient. I just ask AI, does the searching for me, finds the papers. People wrote about these kind of things. It's just that, you have to chase the links and stuff. So, anyway, so series, okay, infinite sums. I'm going to start with, I'm going to be, again, biased toward functions, because that's what we're really going toward. So if I have a set x, then I'm going to define a formal series of real valued functions on x to be an expression of this form. Infinite sum of f sub n, where f sub n is a sequence of functions on x taking real values. The point here is that even though there's an infinity involved here, I am allowing myself to write this down formally without worrying about whether or not this makes sense as a function in and of itself. Okay? So the professor from whom I took this class, he used to say, you can write whatever you want on the board. The board is not going to object to what you're saying, what you're writing. But then it's a different matter whether or not what you wrote makes sense. It's kind of, I mentioned this last time, the last time I taught this as well. This kind of reminds me of a Bruce Lee quote, actually. In one of the movies, he's like, you can hit a board, the board doesn't hit back. Like the same thing in math here too. But of course, the point of doing this is we would like to be able to write expressions of this form and then do some stuff and realize under certain circumstances, if x, y, z, whatever happens, then in fact, this is a valid real number, real function, whatever. Okay. I'll give a couple of examples. Oh, let me say this. Of course, instead of just looking at a sequence of functions like this, if I were to say, for instance, think of capital X as a set consisting of one point only, well, functions from one point into reals, you can pretty much think of this as just reals. Okay? So you can think of formal series of real numbers also. I'll write it here. Formal series of real numbers. And I'll say this too, instead of having the terms that you're considering coming from a set of functions or reals, whatever, what you really need is, well, some set, presumably with some sort of a metric, on which you have some sort of a way to combine multiple elements. The way to say this, more formally, is the structure is what is called a metric group. I'll leave it to you to figure out what the definition of this is, because we're not going to use it. OK. So before going any further, here are some examples, the most important examples for our purposes. So for instance, I can think of this. So for instance, one family of infinite series like this, formal infinite series, is what is called the geometric series. Okay, now you're looking at this. Alpha, some real number. For each alpha real number, you look at this sum, without really worrying about whether or not this converges, diverges, whatever. Formally, you're just looking at this expression. Okay? This is going to be the best kind of series for us. The second kind is what is called the harmonic series. That's another family. Maybe it's not a family, but I guess this is the sum of reciprocals of integers. I'll just write it like this, Riemann zeta function. We had defined this before. Riemann zeta function. This is not quite a function at this stage. I'm thinking of it as a formal series. It depends on one parameter, s, from 1 to infinity, 1 over n raised to the power s. S, some real parameter. For each s, you have a different infinite formal sum. And the notation for this typically is zeta of s. The point being, of course, is that somehow we would like to be able to say, oh, this thing converges, and really I should be able to think of this as a function of s. So even though I put function here in quotation marks, eventually we would like to be able to turn this into some sort of a function. And indeed, there's a famous problem, Riemann hypothesis. It's all about understanding the properties of this sum as you vary s. Okay, that's the second example. I'll write the Riemann hypothesis here too. You can look it up. Third, well, if I have a C infinity function, I have the Taylor series for it. Again, as a formal series. Here, x star is arbitrary, say real, and f is an arbitrary infinitely differentiable function. Okay, these are the three main examples we should look into. I'll give one more, in fact. There are other situations where you allow sort of negative indices as well. There are things like Laurent series, whatever, where you have functions that have poles and stuff. We're not going to discuss those, although those of you who are going to take complex analysis are going to be worried about this. I'll add one more example that is slightly more complicated. Here, at least from an abstract point of view. Example, or maybe exercise. Say I look at the collection of homeomorphisms from the unit interval to itself. Okay. This is what is called a group under function composition. If I were to take two homeomorphisms, compose them, that's again a homeomorphism. And if I have a homeomorphism, so is its inverse. So I can say this set, together with the composition operation, is a group. And I can turn that into a metric group. Metric group basically means this composition operation, together with inversion, should be, well, continuous with respect to some sort of a metric. You've seen how, if I were to just use a C0 metric, this doesn't quite work. The trick is, you look at the C0 metric between the two homeomorphisms together with the C0 metric between the inverses. This is the natural distance. This d bar makes this into a metric group. Is a metric on homeo 0, 1, making it, in fact, a complete metric group, making it a metric group. In this case, I cannot just add homeomorphisms and expect to get a homeomorphism, but I can certainly take a sequence of homeomorphisms and keep sort of composing them. And so I can look at formal compositions like this. Compositional series of homeomorphisms. You can do something like this too. We're not going to deal with this part. These are all sort of in the same direction. Any comments or questions so far? Okay. Now, we should be able to say things about how to make sense of this as a number or as a function, whatever. So let's define what it means for a sequence, for a formal series to converge, diverge, whatever. Let's look at a formal series, like so. well, maybe I should ask you, how can I perhaps make sense of this being convergent or divergent? I want to define what it means for this infinite sum to converge or diverge, say for a sequence of numbers, say in this case, geometric series.
For any epsilon, there is a capital N such that the sum of all functions evaluated at that point up to, or at n greater than n, is within an epsilon?
Essentially, of course, expert advice when people ask you something like this, don't go for the epsilons and stuff. Okay. Clearly, I'm not. It's not really reasonable to expect epsilons and deltas. What you can say is, well, look at the sequence of truncated sums. Don't take it all the way up to infinity. Take it to 1, 2, 3, whatever. So this was the sequence of partial sums. Okay. Call this convergent if that sequence of partial sums converges, and define this to be the limit. Okay. Is called convergent. So this formal series is convergent if, I'll write it like this, the sequence of partial sums k from 0 to n, this sequence of functions or numbers, whatever, is convergent. In this case, we define this to stand for the limit. Okay? So when you have a formal series that is in fact convergent, it is a true thing, true function, true number, whatever. In this case, we also write we define this to be the limit. F sub k. Okay? So there's a notational sort of overloading here that you have to be careful about. When you look at an expression like this, it on the one hand represents a formal expression like this, but under certain circumstances, it also represents a true limit in the way we discussed. It could mean both. Okay. Okay. But of course, if you look at this sequence, this is a sequence of functions. And so I'm talking about the limit of a sequence of functions. At this point, we know there are multiple ways in which this can happen. So depending on the case, we would either call it pointwise convergent or uniformly convergent. Okay. In the case of a sequence of real numbers, of course, there is no distinction pointwise versus uniform. Okay. Now I'm going to define something else. I'm going to call this infinite sum, formal sum, absolutely convergent if not this only, but in fact, the sum of absolute values converge. Absolutely convergent. Okay? If the sequence of partial sums, well, I'll write it like this. If this formal infinite series is convergent, if the formal series with absolute values if the formal series n from 0 to infinity, f sub n in absolute value converges. Okay, and since these are again functions, I should be looking at absolutely pointwise convergent, absolutely uniform convergent, absolutely uniformly convergent. Okay. Sometimes you might see the phrase conditionally convergent if you have a formal series that is convergent but not absolutely convergent. There are series like this we're going to see later. Convergent but not absolutely. And in the other case, if none of these happen, you call it divergent. Okay? I'm defining these, but certainly we're going to first focus on these two cases. That is to say, we're going to focus on a series of numbers, do some calculations, some examples, and then next week we're going to really transition to the case when we're looking at formal sums of functions. Because ultimately, something like this should be very important for us. Any comments or questions about any of this so far?
Why do you have to specify formal series instead of just say series?
Because I would like to remind myself that this need not be an actual function.
Series is not function.
Plug in s equals 1. That's infinity. Okay? Let me put it this way. Physicists tell you that you should be able to plug in s equals minus 1 also. When you plug in s equals minus 1, you're adding all integers, but they don't want that sum to be infinity. They want it to be minus 1 over 12 for whatever reason. So just to keep my sanity, I'm reminding myself, this is a formal series. Okay? I'm allowing myself to write this expression without worrying about whether or not it means something numerically or functionally. We'll get there later. You don't have to say it. I'm just going to say it. Okay. Any other comments or questions? Okay, let's do examples. So for instance, let's first start with the geometric series. Geometric series is really the main example you should focus on, okay? You really need to understand the difference between this for different alpha values and this guy. Once you understand these two families, you're pretty much good for the rest of this course. And I'm going to take my time, do some calculations explicitly. Okay. I have this formal series of powers of alpha. Okay. Alpha is some parameter that I'm going to worry about later. I'm trying to investigate if this formal series in fact converges and for which alpha values. Okay. For some alpha values it's going to converge, for some alpha values it's going to diverge. For instance, if I were to plug in alpha equals 1, then I'm just adding 1 infinitely many times. That's going to diverge to infinity. Or if I were to plug in alpha equals -1, for instance, then it would, right, so let's write a couple of examples. Then the nth partial sum, so if I were to truncate this infinite sum all the way up to n, now this would be an honest to heavens finite sum, which I can calculate. Right, so if I have n terms, because I'm starting from 0, that s sub n is going to be n plus 1. Okay. In fact, what I can say also, if you want, is that this is big O of n as n goes to infinity. So ultimately, for alpha equals 1, the sequence of partial sums diverge to infinity at a linear order. Okay? So alpha to the n, and from 0 to infinity, diverges. Diverges linearly, if you want. Doesn't diverge faster than n. Okay. If I were to plug in alpha equals -1, then what happens in this case? So -1 to the 0 is +1, -1 is going to be the next one, right? Because n is going to oscillate between odd and even. If I'm looking at odd and even exponents, powers of -1, that's going to alternate between plus and -1. Okay? So s sub n is going to alternate between 1 and 0. So I think if n is even, s sub n is 1. If n is odd, s sub n, partial sum all the way up to n, is 0. So this sequence of partial sums is just an alternating sequence that alternates between 0 and 1. Consequently, it is divergent. Okay? Okay? Does this make sense? How about other values? Let's try to argue like this. There is one trick here that you can use to write, write the nth partial sum as a formula. And so, for instance, what you can do is this. S sub n, right, is the sum from k equals 0 all the way up to n of alpha sub k. Okay, so this is 1 plus alpha squared plus dot 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 plus alpha to the n. Okay, I'm going to give you the trick, and this trick ends up being very useful all over the place. Okay, so even if you don't remember it, the formula, at the very least, remember the rule. I'm going to multiply and divide by 1 minus alpha. I'm assuming, of course, for this to work, that alpha is not equal to 1, because otherwise I would be dividing by 0. So say alpha is not 1. If alpha were 1, the analysis was fine anyway. And so if I were to do this, okay, in the numerator, what do I have? there is some sort of a Newton cradle thing happening here. Right? If you were to expand this, you have 1 plus alpha squared all the way up to alpha to the n minus alpha squared minus alpha raised to the power n plus 1. Okay? So that's the formula. That's a closed form. Okay? What is the beauty of this or benefit of this? So what we proved is that for any alpha, if alpha is not 1, then the partial sum gives me this. Well, for fixed alpha, in order for me to be able to say whether or not the associated series, this guy, converges or diverges, well, I'm just going to take n to infinity here, right? Because I'm just going to look at the partial sum, take n to infinity. Yes? But I can say here, the only thing that does change with n is this. And I know that since I'm taking exponents, this part is going to go to 0 if alpha in absolute value is less than 1. Otherwise, it's going to diverge. Okay? So I can write it like this. And in fact, I also know a specific value, right? If alpha in absolute value is less than 1, the limit of this, as n goes to infinity, is going to be 1 over 1 minus alpha. Okay? Maybe this, after this, it kind of makes more sense to talk about formal series and series. Right, so I would like to be able to look at this expression without really specifying a specific value for alpha. But for certain values for alpha, this sequence of partial sums alternate between plus or minus, or plus 1 and 0. I still would rather write this, is the point. So this side is a formal series that happens to be a convergent series conditioned on certain values of alpha. Okay? Questions or comments about this? You should have seen this formula in Calc 1 or Calc 2, whatever. Okay. Probably you've seen the other results for the second one also, but let's try to go ahead and try to do things. I want to do zeta of 1, and I want to justify somehow that zeta of 1 is divergent. Okay? If I were to look at the formal series of reciprocals of integers, that should be a divergent formal series. And I think this is what is called a harmonic series, like sum of the reciprocals of integers. Anyway, so this I'm thinking of as an infinite sum. And I claim that this diverges. Okay, this is not a well-defined number. Okay, again, in order for me to be able to say something like that, what do I need to do? Well, I'm just going to truncate this infinite sum, and I'm going to add finitely many terms. And I'm going to justify somehow that this sequence of finite sums, they don't stabilize anywhere. OK. So let's look at this. S sub n. OK? This is a sum of reciprocals of all integers all the way up to n. OK? So 1, I'll write it like this, plus 1 over 2, plus 1 over 3, plus 1 over 4, plus 1 over 5, plus 1 over 6, plus 1 over 7, plus 1 over 8. And then 1 over 9, 1 over 10, 1 over 11, 1 over 12, 1 over 13, 1 over 14, 1 over 15. There's a trick that I'm going to use. That's why I'm writing this explicitly like this. 14, 1 over 15, plus 1 over 16. And then it keeps going on like this for large enough. And ultimately, I'm going to be left with 1 over n. OK? So how did I separate these? Well, I separated them based on powers of 2. OK? So this is 2 to the 0, and then 1 over 2 to the 1. And then I separate it until 1 over 2 to the 2, 2 to the 3, 2 to the 4, and so on. So in a sense, even though I'm adding reciprocals of all integers all the way up to n, I'm separating them on a logarithmic scale. OK? Here's a nice trick here. By the way, I could have used powers of some other integer too. It doesn't really matter that much. This is, I think, the way it was written in the textbook. But here's a trick, OK? I'm going to leave this as is, leave this as is. If I were to replace this 1 over 3 by this, the sum would decrease, because 1 over 4 is less than 1 over 3. I'm going to likewise replace all 3 of these by 1 over 8. Again, it's going to decrease. I'm going to replace all, I guess, 7 of these by 1 over 16 and so on. In fact, like this, 1 plus 1/2 plus 1 over 4 plus 1 over 4 plus. Now I'm going to have 4 times 1 over 8. I'm going to have 8 times 1 over 16, and so on. And then ultimately, we can think of it like this. Okay? So here's 1 to whatever. Here's n. But given any n, there's a largest p such that 2 to the p is the maximum power of n, less than or equal to n, something like this. And here it's going to be 2 to the p plus 1. OK? So you see I'm looking at the logarithmic scale here, or exponential scale. There's going to be some terms here, but at the very least, I'm going to have a lower bound coming from each of these pieces. OK? I'll just leave this part. What is the point of doing this? Well, note that this gives me a lower bound on the nth partial sum as 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2 and so on, p many times. So at the very least, so 1/2 times how many of them? P many of them. Okay, p is a function of n if you want. The point of this is that as you take n to infinity, okay, this is going to go to infinity. Therefore, there is no way for S sub n to stabilize at a finite point, finite number. what did I do? Instead of looking at the partial sums of this, I came up with something that was a lower bound. That was easier for me to compute. And I showed that that lower bound blows up. Well, if your lower bound blows up, the thing itself has to blow up also. Okay. Any comments or questions about this?
Can you explain P again?
I fixed an n. Okay. I'm looking at the nth sum. Look at this set, non-negative integers p, such that 2 to the p is less than or equal to n. This is a set of integers. Say S of n. That's a set that depends on n. Okay?
It's a set.
Yes, it's a set of all those integers p such that 2 to the p is less than or equal to n. Okay? It's a bounded set. By the well-ordering axiom, it is a max, which is an integer.
So does the set means partial sum?
No, no, no. I'm just taking the integer n because I am separating the reciprocals of sums all the way up to 1 over n according to powers of 2. And I'm trying to figure out how many sort of lumps like this I have in the partial sum.
Where's the lower bound?
This one? What I did is this, okay? I realized that the sum of all reciprocals all the way up to 1 over n can be separated in this fashion. Okay? So if I had, for instance, n equals 15, I would just look at these terms for n equals 15. Okay? And then what I did was, well, according to the different sort of classes of these reciprocals, if I were to decrease these terms that are not powers of 2, or reciprocals of powers of 2, and if I were to replace those reciprocals that fail to be reciprocals of powers of 2 by the appropriate power of 2, well, for instance, 1 over 3 plus 1 over 4 is lower bounded by 1 over 4 plus 1 over 4, which is 1 over 2. And likewise, 1 over 5 is less than or greater than 1 over 5 is greater than 1 over 8. This is greater than 8. This is greater than 8. So if I were to replace all of these by 8, that would be a lower bound. But that is 4 times 1 over 8, which is 1 over 2. So each of these lumps, I was able to lower bound by 1 over 2. And that's how I get this. Because there are p many lumps like this. Okay, I wanted to say more, but let's leave it here. We're going to continue on Friday with further calculations. Thank you. All right, let's start. Good morning. We're going to keep working on series, numerical series still. I still have a couple words to say about zeta. Just to remind you, we did this. This was the geometric series. For any alpha, we're just looking at the formal series, that is the sum of all powers of the same number alpha. And then we realized that this sum converges if and only if alpha in absolute value is less than 1. And indeed, it converges to the number 1 over 1 minus alpha. And we saw that this diverges otherwise. So this is the geometric series example. And the other one is, I think this is the harmonic series, or in Calc 1 you might have heard the phrase P series. It's the same thing. So for any s real number, I'm thinking of zeta of s to be this formal series. That is to say, the s powers of reciprocals of integers added up. And then we argued that zeta of 1, that is to say, if I were to just take the sums of all reciprocals of all integers, that's going to diverge. I want to calculate a couple more things and indeed show that zeta of s in fact converges if s is any number greater than 1 to begin with. And then I want to say a couple more words. I want to think a little bit more about this example, and then we'll be on our way. Let me see. Yeah. OK. So for this, I claim that if s is greater than 1, then in fact, this infinite sum converges. That is to say, if I were to look at the partial sum sequence, that sequence converges to some real number. So I'll write it here. For any s greater than 1 as a real number, zeta of 1 is a convergent series. Zeta of s is a convergent series. And remember, we called a formal series absolutely convergent if the series of the absolute values of the terms were convergent. Well, in this case, all of the terms are non-negative to begin with, which means convergent in this case is the same thing as absolutely convergent. And likewise, I could have said this is absolutely convergent. Oh, but then again, yeah, exactly. So maybe I should write that as well. So this, insofar as alpha is less than 1 in absolute value, again converges. And it converges to this number. For alpha less than 1 in absolute value. So this series is absolutely convergent. Okay. This is to say, when I'm looking at convergence or absolute convergence, in principle, for absolute convergence, I'm looking at a different series than the original series. And I'm not requiring that the limits be the same. So if I were to choose alpha to be -1/2, in absolute value, it would converge to a different number. So that is allowed. Okay? I'm not saying that this has to converge to the same number. I'm saying it has to converge for absolute convergence. That's a small difference. OK. Now, let's try to argue. So what do I need to do? I need to first truncate this infinite sum. Say I look at this, x sub n s. Say it's this. 1 over k to the s. Well, the nice thing about this is that, of course, I can think of pretty much any, in fact, any finite sum as the integral of some step function. And if I were to interpret this as the integral of some step function, then I can try to sort of use some integral calculus, whatever, to try to come up with some sort of bound. Okay? And so what I can say is this. I can define sigma sub n of s, n and s, from 0n to reals. That takes an x, sends it to the minus s power of the ceiling of x. Okay, what is the ceiling of a real number? It's the smallest integer greater than or equal to x. Okay. Now, how does this look like? 1, 2, 3, 4, 5, let's say. So for instance, sigma sub 5s would look like this. I'm sampling out the heights from 1 over x to the s. Say this is this function. Okay. This is this. And then my function is going to look like this. So between 0 and 1, it is this. Because if I were to plug in x, some number between 0 and 1, the ceiling of it is 1. So the smallest number, smallest integer, greater than or equal to any number here is 1. So I'm just looking at 1 here. Then between 1 and 2, the ceiling is going to be 2. So I'm going to be looking at this. Then I'm going to be looking at this, and so on. Okay. The point here is that this is a step function. And its integral is the nth partial sum. And the integral from 0 to n of sigma is precisely this finite sum. Um, 1 over k to the s. Okay. Now what I want to do is, well, by definition, by definition, 1 over x to the s is some function that is certainly differentiable, or rather, that is Newton integrable. It is an antiderivative that dominates the step function. So if I were to replace this function by this, the integral would give me an upper bound. Okay, that's what we're going to do. There's one problem here, though. And the problem is, even though this is a Newton integrable function, well, here it blows up. And indeed, here, the integral of this is infinity. But what I can do is, instead of trying to control this whole thing, I can just look at this integral. So I can just split this as 1 plus integral from 1 to n. I am allowed to do this. And this I can upper bound. By the integral of this. Okay. Oh, that should be 1. Well, here, between 1 and n, this is a very nice function. It is, in fact, infinitely differentiable, all that stuff. FTC2, whichever fundamental theorem of calculus, would tell me that it shouldn't matter what this integration theory is. Pretty much everyone should agree. Okay? And in fact, I can also evaluate this. And I can indeed realize that this is the, so I can just guess an antiderivative for this using calculus methods. For instance, I can say this is, oh, missing up pluses and minuses here. X to the minus s plus 1 divided by minus s plus 1 differentiated. So this guy is an antiderivative for this. At this point, I can use whatever integration I want. I can say Newton, HK, all that stuff. In any event, I know what this is going to show up as. this is precisely going to be this function at n minus the same function at 1. So 1 over 1 to the something is just 1. So this. Okay, and then I can, if I want to consolidate a little bit, and leave it like so. Okay. So you see, this is an upper bound on the partial sum, all the way up to n. But since I'm assuming that, yeah, s is greater than 1, that means that minus s plus 1, right? So if s is greater than 1, then minus s plus 1 is less than 0. It's a negative number, which means as I take n to infinity, this guy is going to converge to something. And indeed, it's going to converge to 1 plus minus 1 divided by this. So this is just 1 plus 1 over s minus 1, which is just, if my math is correct, s divided by s minus 1. Okay? So for any s greater than 1, I was able to show that the nth partial sum is upper bounded by this expression that doesn't depend on n. Okay? And this is a finite number. From this, can I conclude that zeta of s has to be convergent? I need to say something. I was able to come up with just an upper bound. Let's think about this for a couple minutes. I came up with an upper bound that certainly depends on s, but I'm talking about whether or not this converges once I fix an s. So s is a fixed parameter, and I'm taking n to infinity, right? Can I justify, can I conclude from just this bound, that this is bounded by this, that the sequence of partial sums has to converge?
Do you need to find a lower bound? Or the same?
Okay, let me just check the, yeah, go ahead.
Only increasing, so that should be convergence.
Okay, so we have two ideas. One of your colleagues say this should be converging. Another colleague says, no, you need to do more.
Is it possible oscillate never?
Is it possible?
I have to consider.
What do the rest of the class think? Either it converges or it diverges, or maybe it converges but you need to say more. Okay, I'll give you a hint. Let me put it this way, okay? So once I fix the s, this is even though it looks rather complicated, it's a sequence of real numbers. Okay, so far I was able to show that this sequence of real numbers is bounded. But what else can I say about this sequence of real numbers? Yeah. No, yeah, do you have anything to say?
Is it dealing with monotonicity?
Yes.
It's just strictly decreasing now.
Well, I mean, it's strictly increasing.
Oh, okay.
Yes.
The sum.
Yes. So we had a couple of results when it comes to sequences of real numbers, right? So we had the Bolzano-Weierstrass. Any bounded sequence has a convergent subsequence. We had, what else did we have? Monotone convergence theorem, which said that if you have a non-decreasing or non-increasing sequence of real numbers, it always converges to the sup or inf. Of course, the sup or inf could be infinity or minus infinity, but in this case, I was able to show that the sup is a finite number. I'm not saying that this is the sup, by the way. I'm saying the soup is some number that is upper bounded by this. In principle, I don't know that it converges to this. Did we have any? I feel like we had another result about sequences. Monotone convergence, Bolzano-Weierstrass. Well, these are the two I can remember right now. And in any event, monotone convergence certainly is sufficient. Let me just write it out here. So far we have that for any s greater than 1 and for any n, the partial sum until time n is upper bounded by this expression, which is a finite number. And furthermore, since each of the terms that I'm adding up are positive in this case, or more generally non-negative, I know that this sequence, so it's a sequence of n, is strictly increasing. It is non-decreasing. Okay. So by the monotone convergence theorem, I know that this guy converges to its soup. And that soup has to be upper bounded by this. Yeah, let's write it like this. By monotone convergence theorem, zeta of s, which is this now convergent sum, is the limit of this, by definition, 1 over k to the s. Oh, it's an n. Which by MCT is a soup of these sums. As you vary n, 1 over k to the s, which is upper bounded by this, which is a finite number. Consequently, zeta of s is a convergent, and in fact, absolutely convergent series. Okay? And so I hope this also justifies why it's a good idea to see if the terms of, if the series of absolute values of terms is an important series. One of your colleagues mentioned, oh, maybe there could be some sort of cancellation happening, oscillations happening, whatever. But the point is, instead of looking at a series like this, and instead of trying to figure out if this converges or not, what you can do is you can first figure out if this converges. So you would ask more. The point is, it's often a lot easier to figure out if this converges, because you're canceling all these possible oscillations that can happen. And so that's why absolute convergence is an important idea here, is what I'm trying to say. Now, of course, it is not always the case that just because a series converges, it is also absolutely converges. So absolute convergence is a notion that is strictly stronger. We're going to see examples of that. But at the very least, under certain circumstances, it works a lot nicer. Okay? Helps with calculations. Any questions or comments about this? Yes?
So this case never oscillate?
Well, yes, because each term that you keep adding is a positive term. It only goes in one direction, this finite sum. But for instance, zeta of 1, if you were to adjust it like this, you can try playing around with this. So this doesn't converge absolutely, because if you were to take the absolute values, you would just get zeta of 1. And we just showed that this diverges if you were to plug in the absolute values. We did this on Wednesday. But what I'm saying is that this is in fact convergent.
In that case, S is 1,
Exactly.
but your definition S has to be greater.
Exactly. But this is not zeta of 1. I have minus 1 to the n. I'm including oscillations, which causes somehow this pluses and minuses to cancel out just sufficiently enough. Okay? Maybe you've seen in Calc 2 or whatever alternating series test. It says that if you have a sequence that converges to 0, then this always converges. We're going to see this as well, hopefully. Probably next week. Okay. I want to leave this aside for a while, though. Any other comments or questions about this part? Okay. Now, I want to say two more things about these two examples. First of all, let's try to deconstruct some idea here. Well, so far, when we were computing integrals, we were always computing them on compact subintervals of whatever. Okay, so for instance, in this case. But I might as well think of the limit of this expression, for instance, as n goes to infinity, as the integral from 1 to infinity. That's an improper integral. Some of this improper integral theory is in the textbook. So I decided not to spend that much time. It's a beautiful subject, whether or not certain improper integrals converge, diverge, whatever. But I just wanted to mention, so this is sort of like the starting point in a sense. We don't really need to talk about improper integrals for most purposes, but we could if you wanted. So what I can do is, maybe I'll give it as a large exercise. Say I have some locally integrable function defined on the whole reals. Okay. Define improper integral as the limit. So right, so I'm just going to take some, say, large closed and bounded interval, and I'm going to take the endpoints to infinity, plus and minus. Say lambda rho f of x dx. Okay, and I'm going to take the limit of lambda as it goes to minus infinity, and rho as it goes to positive infinity. Okay. It's a beautiful subject, but I decided to let it go because there are certain technicalities. So for instance, there are certain issues with synchronizing the left and right endpoints. For instance, if you were to think about the sine function, if you were to try to integrate it over the whole reals, that in fact is divergent. But if you were to only consider symmetric intervals, minus n to n, well, sine function is an odd function, so the integral there is going to be 0. So if you synchronize the endpoints, the limit ends up being well-defined, and it would be 0. So this is what is called the Cauchy principal value. there's a bunch of like technicalities. I decided to let all of these go because at this level, if we try to study them, it kind of looks like a lot of these things are ad hoc, and like we would need a lot more understanding of these weak derivatives and stuff like that. So somehow, in a surprising way, if you were to synchronize the endpoints and then take the limits, that is, in a sense, some sort of a weak differentiation. Okay. Of course, for application purposes, improper integrals are very important, but takes more effort, and I decided to let go and study more things, other things. I should mention improper integrals, like when you think about it, if you're trying to integrate this according to Riemann, right? So you're going to fix your interval. Then for any epsilon, there is a delta such that if I were to take a sampled partition of this interval that you chose, the Riemann sum is approximately this number. But then on top of that, you're going to take two more limits. That's going to change every other choice that was required to even compute this integral for Riemann. Okay. Now it turns out that, in fact, another benefit of the Hake integrals is that it also solves the issue with improper integrals. So if you want to learn more about this, there's like a chapter, there's a section in the Fonda textbook, and there's a theorem called the Hake Theorem. It's about this. Otherwise, improper integrals, if you're just using Riemann integration or Bourbaki integration, it's rather cumbersome from a technical point of view to develop the theory and all that. OK. Just wanted to mention it. Now, any other questions? Are there any questions about this? Yes?
You mentioned synchronize.
Yes.
Is it symmetrical?
That's what I'm saying. It's like, for the improper integral, so the vanilla improper integral requires that these are independent. So you take this limit independently and this limit independently. But if there is some relationship, so if there's a correlation between the sort of endpoints, then you're in fact looking at a more restricted limits. You're looking in fact at a distribution. Yeah. Okay. Now the second thing I want to discuss is not about this, but it's really about the first example, the geometric example. Because remember, I defined infinite series of functions and numbers or whatever. And one of the sort of general examples I had mentioned was, well, the formal series, that is the Taylor series of some infinitely differentiable function. And so somehow, we can also think of this example from the perspective of Taylor approximation. Okay? Because think of the following. For an arbitrary alpha, this side is a formal sum, formal series, that we showed is convergent, and it converges to this honest to heaven's number, 1 over 1 minus alpha, insofar as alpha is less than 1 in absolute value. Of course, I can think of, instead of writing alpha, I could have written x. And I could have said, oh, I have this function 1 over 1 minus x, which somehow ends up being the same thing as the infinite sum of powers of x. Okay? Oh. So the middle example continued. So this. Consider the function. So consider the interval minus 1 to 1. And the function defined on it that takes an x and sends it to this. Okay? That example, so that calculation that we did before, told us that in fact for any x in I, this is f of x. Okay? And in fact, this is a pointwise convergence, is what we showed. So the sequence of functions that at time n takes an x and sends it to this converges pointwise to f. In fact, if you were to look back at the calculations that we did, we showed that this, so let's call this perhaps f sub n. Right, what was this? So we multiplied and divided by 1 over x. And then this gave us, so 1 plus x plus whatever, all the way up to x to the n, minus x minus whatever, whatever. So it's this. So even though I wrote this function like this, once we realize, we can just do some algebraic manipulations, f sub n is this function. And I can just look at this distance. Okay, what is this? This is this minus this, which is nothing but x in absolute value raised to the power n plus 1 divided by 1 minus x. So for instance, what I can say here is that insofar as I look at convergence of f sub n to f on any compact subinterval, the convergence in fact would be uniform, because on any compact subinterval of -1 to 1, this would have an upper bound. So what I can say is that in fact this is uniform on each compact subinterval. Generally, it is pointwise. The interval is open, but if I restrict my attention to any compact subinterval, say -1 to 1 endpoints included, then the uniform there, so the convergence there would be uniform in x. You would get a uniform convergence. Okay, we're going to discuss these issues next week more in detail. I just wanted to mention. And furthermore, in a sense, I can start with f and come up with this sequence as well if I were to just look at Taylor approximations. I want to leave this here. So if I want to compute the Taylor approximation of whatever order, what do I need to do? I need to compute the derivatives. And this is a very nice function. You see, it's the ratio of two polynomials. It's a rational function. It's infinitely differentiable. So I can look at the Taylor polynomials. And so if f of x is this, then the first derivative, right, is minus 1 minus x raised to the power 2, and minus 2, and then I have a plus here. Second derivative, so the first derivative of this is, so minus 2, but I'm going to have another minus here, so that's going to be 2. 3. And I'll leave to you to verify that by induction, the nth derivative of this function is going to be n factorial times 1 minus x raised to the power minus n. Okay. Well, that means what are the derivatives at 0? So x star is 0, say. Then the nth derivative at 0 is n factorial. This is just going to give you 1. And in fact, maybe I should write it like this. Nth derivative divided by n factorial is 1. Therefore, the nth Taylor polynomial of this function at x star equals 0 at the origin is precisely this. Make sense? And so somehow, in this case, we have this function. It is infinitely differentiable. And if I were to look at the infinite Taylor approximation, so imagine t sub infinity perhaps, so the formal Taylor series, well, it ends up being the same thing as the original function. Okay, so you see, this is an important property that we're going to discuss next week, and this is really pointing to this analyticity property of this specific function. Analytic in the sense that you can analyze a function into its derivatives. Okay, and speculatively, I think the reason why analysis is called analysis is because people were interested in understanding these types of situations initially. Okay. Any comments or questions about this? I'm still, giving some sort of a preview as to the infinite series, so the series theory. There is one more thing we can say about this, namely that, well, this expression, this function, is defined on a larger subset of the reals. In fact, this is defined insofar as I'm not plugging in x equals 1. When x equals 1, this blows up. At any other point, it is well defined. It's a nice function. It is infinitely differentiable. I'll add it here. Consider M to be R take away 1, so the complement of the singleton 1. And I can define G to be the function that takes an x and sends it to 1 over 1 minus x on this whole set M. Okay. Now, M is not an interval. It's not an open interval, but it's the union of two open intervals, if you want. And we have that G restricted to minus 1, 1 is that function. Okay. So maybe I should write it. And M is not an open interval. But still, it's something like an open interval. It's the union of two open intervals. I had defined this a while ago. We would say M is an open subset. And it turns out that pretty much all differential calculus, all the theory, applies to functions defined on open subsets of the Euclidean space, of reals in particular. And so one can do differential calculus So there are certain things that you need to be a little bit careful about. But many results do generalize to functions defined on open subsets. Okay? We'll just add it here. One can adapt differential calculus to open subsets of reals or more. Okay. Some of the items end up being slightly more technical, but it is fairly standard at this stage to really do differential calculus on functions defined on opens. And in fact, so those of you who are going to take 30 to 20 are going to sort of learn how to handle open subsets. And indeed, the true sort of way to, so the true habitat for differential calculus is, what is called a manifold, smooth manifold. And indeed, open intervals and open subsets are rather specific examples of manifolds. Okay? Or manifolds. So in 30 to 20, we don't discuss manifolds that much, but in more advanced contexts, you end up needing to do that. So somehow, if you know some physics, doing things on open subsets or open intervals is something like special relativity. But when you want to transition to general relativity, now you end up needing to study calculus on manifolds. Okay. The point being is that it makes perfect sense for me to look at this specific function and think of it as an infinitely differentiable function on M. Okay? And I can write it like this. G is C infinity from M to R. Okay? The point is that even if I don't plug in this expression some input value that is between -1 and 1, I can still go ahead and look at the Taylor approximation, whatever. That would give me a different series. But the point is that since this function is real analytic, all I'm doing is I'm just looking at higher order Taylor approximations at different base points. It's just that the series changes. Okay? Just like the derivative changes at different points, so does the series. Okay? So somehow these real analytic functions are those C infinity functions such that their Taylor approximations at any point converges to the function itself. Okay. Any comments or questions about this? Yes?
If x is greater than 1, this all does not apply.
No. Say x is 15. Okay? This formula is still well defined. So the only case when this is not defined is if x is 1. Yeah, that is a confusing thing. So forget about everything here. Just start with this function. You can differentiate this infinitely many times at 15. Look at the Taylor approximation at x equals 15. You can write the Taylor series. It would give you a different series than this, but it would be the same function. Yes. And in fact, this also points to why I was referring to formal series and stuff. And this is one of the reasons why algebra is so powerful. So you can start with polynomial expressions or infinite series like this without really worrying about, oh, does this converge to something? But those mathematicians who are more algebraically inclined do this, okay? They look at a certain formal series with no regard of convergence, divergence, whatever. And then based on the formal expression, they deduce the existence of some sets on which this formal series is an actual function. So out of functions, they create space. Or, out of formal expressions, they create space. Very bizarre. Yes, it's very bizarre. OK. Any other comments or questions? I think I want to do one final thing. It's a nice little test. So I told you how in the business of infinite series, we would like to be able to come up with certain criteria that we can apply to the terms that we're adding that would allow us to deduce that, oh, in this case, the series converges, whatever. One of the most simplistic ones among these tests is what I call the term test. That is to say, it says this. If you have an infinite series that converges, then the terms have to converge to 0. OK. This was just, I was trying to give you some, sense as to what comes after. Probably we're not going to be able to cover all of these in full detail, but at least this is some sense. So let's say this is a theorem, term test. OK, this is one-sided only. It says this. Let this be a formal series. If it converges, then the sequence of terms converges to 0. Certainly not the other way around. Zeta of 1 is an example. Just because the terms converge to 0, you cannot just deduce that the series converges. Okay? It goes one way only. And it's a rather straightforward, it is a rather straightforward proof, because out of this sequence of partial sums, I can extract the nth term. Namely, the nth term here is nothing but the partial sums all the way up to n minus partial sums all the way up to n minus 1. Okay? And I'm saying this converges to something, and certainly this has to converge to the same point. This goes to 0. Okay, that's the proof. Okay? And we're done with this week. Have a nice weekend. We're going to continue next week with more of these.